Well, good morning, maybe afternoon for some of you. Um, this is the webinar series on better buildings, and we are happy that you could join our webinar today. Let's get started. Hello and welcome. We are dedicated to bringing you the latest information about the leading industry experts in leading technologies in space conditioning. Thank you again for joining us. Next, please. So today we're talking about storing and saving using thermal energy storage in commercial buildings, and talk a little bit about this technology for all of you. Next, please. And that's me. I'm Marcus Bianchi. I'm a senior research engineer in the National Renewable Energy Laboratory and Buildings Technologies and Science Center. I'll introduce you the team, and I'll give you the agenda next. Next, please. So we'll start with just an overview of the space conditioning, and then some information about the thermal energy storage. There'll be some polls just to make sure that we have the right audience and what we know about that. And then we have the speakers, and then a Q&A in the end. And the Q&A will be something that, if you can, during the presentations, provide, like submit some questions, we'll try to keep answering as we go. Next one, please. Just like some space conditioning technology research team updates to start. Next. The team is myself, Dr. Michael Derue, who has been working in the space conditioning technology research team from the get-go, Kelsey Dombrowski, and Chuck Putin. All of us work together to provide some of the information that is related to commercial buildings and space conditioning. Very important, if you would like to join our mailing list, please send an email to bba.spaceconditioning@nrel.gov, where we'll include you in the mailing list to receive updates as we make them available. Next one, please. Just to give you like an overview of the resources that are available, we have a series of guides that we publish both in English and Spanish to actually reach building owners and facility managers in multiple languages. Those guides are there. You can just go to our website, and actually this one is a link for you to be able to use it. We have a series of webinars. The webinars are usually recorded, as this one is, and those are in the repository of webinars that you can actually access. And then we also keep and maintain the HVAC resource map, which is a repository of like reports, information, new technologies, and so on that comes available. So if you have a chance, do visit it, and a quick search on the HVAC resource map will get you there. We'll have another webinar coming in February to talk about the transition from low GWP and natural refrigerants. How do we get to low GWP and natural refrigerants in the space conditioning? So if you're interested, please sign up for that one too. Next one, please. We'll start by actually telling you that we work very closely with all the teams that are related to systems technologies in the Better Buildings Alliance, and one of them is Renewables Integration Team that it's working with us. There is an initiative which is a consortium that's called Store for Build, which is energy storage in buildings, which I'm gonna just give you a brief overview. Next one, please. Store for Build is an energy storage consortium that looks at ways to connect storage to different buildings and communities. And it's a multi-laboratory consortium. It involves NREL, Oak Ridge National Lab, Lawrence Berkeley National Lab, and Pacific Northwest National Lab, all together working with industry, utilities, and different stakeholders to determine like the different uses of energy storage technologies in buildings. There's information about that, and if you do a search on Store for Build. Next one, please. The Renewables Integration Technology Research Team is another team, just like the Space Conditioning team, that figures out how to include renewable energy technologies in commercial buildings, either for flexibility or generation locally. Tim Leclerc is actually attending this webinar. I'm just doing the introduction, so it makes it like simpler instead of like moving speakers, but Tim will be available to answer questions as we go through this presentation. Next one, please. What is thermal energy storage and why use it? As opposed to battery energy storage, thermal energy storage is essentially the idea of having like not electrochemical storage, but having thermal batteries available. Next one, please. Just to give you an overview, so you can have storage of either like a sensible storage where you have like a liquid or a solid, where you actually maintain it hot or cold for purposes of heating or cooling. In very hot temperatures, you may have it for other purposes like generating electricity, but generally for buildings, we're trying to meet the thermal loads of the building. It's a form that can use directly for heating and cooling. We call it thermal battery many times. And energy can be stored as sensible latent heat or even in thermal chemical storage. Next one, please. Why thermal storage? Because thermal loads vary during the day. And, we try to align electricity consumption with storage in such a way that, there are times that it's interesting to actually heat the liquid or provide, heating to a particular system when it's actually cheaper to operate, let's say, the heat pump. When it gets very cold or electricity prices are very high, you may want to actually use the storage instead of like running a vapor compression cycle, let's say, to do that. So storage can avoid curtailment because you can actually go to it instead of, like using renewable energy as a resource. It can reduce peak demand because you can actually use the storage during the times of peak of the electricity. So rather than actually using electricity to generate heat, you can actually go to the storage and actually extract thermal energy from it. And because of time of use rates, you can actually save in costs by when electricity is on the high price, you can actually go to the storage to provide heating or cooling instead of actually using vapor compression that actually consumes a lot of electricity. There are opportunities to increase efficiency, and with the storage associated with electrified heating, you provide flexibility to the building. Next one, please. Thermal energy storage is just one of the several approaches that we can use to support building electrification and decarbonization. You have generation, you have electrochemical storage, and you have, essentially a community of buildings that can be actually working together to provide that kind of flexibility to be able to electrify and decarbonize buildings. Next one, please. If you please go to Slido, thank you for putting in the chat the link. If you go to slido.com and put pound DOE as the event code, you can actually answer the polls as they come up. So would you please do that? So if you'd like to respond to those polls, that would be great. Okay, so that's the first one. What is your view? We give some time for people to be able to respond. I'm responding too. Thank you. There's a lot of people attending. That's great. Very diverse background. Wow. Thank you. Okay, a little bit more. How familiar are you with thermal energy storage? Excellent. That's great. Yeah, so what are you interested in learning about, and what would you, what topics would be interesting for next webinars? So a lot of people respond. Yeah, if you have others, please edit by writing it. Thank you. Excellent. So today's presenters, we have two presenters today, Bruce Lindsay from Trane Technologies and Kent Marsh from Colorado Mesa University. Next one, please. First presenter is Bruce Lindsay. He's a business development leader in Trane Technologies. Hold on, because I got this as part of Calmac ice tanks in thermal energy storage systems, and focus on the investment tax credits in the U.S. Inflation Reduction Act of 2022. Mr. Lindsay has been involved in thermal storage for over 30 years and was the executive director of the Electric Power Research Institute, EPRI's Thermal Storage Research Center at University of Wisconsin-Madison. He was recently the energy manager for the Brevard County Public Schools in Florida, where he had 84 schools, of which 20 had ice storage systems. He's an ASHRAE Distinguished Lecturer and Program Chair for ASHRAE TC 6.9, which is the Thermal Storage Committee. Bruce, your slides. Thank you.
Next. Thank you, Marcus, and thank you everyone who's joined us today for this webinar. We're rapidly approaching over 1,000, so really good reach out. And I want to thank DOE and NREL for hosting this program. Real quick to start this off, I joined Brevard County Public Schools in 2017. The first day on the job, walked in, sat with my boss. He says, "By the way, Bruce, do you know anything about ice storage?" And I said, "Yeah, I know a little." And he says, "Good." I asked why. He says, "Well, of the 84 schools we have here, 20 have ice storage systems." Wow, that's a lot. How old are they? He goes, "Oh, they're all over 20 years old." So they all still running? And he says, "I don't know. That's for you to find out and for you to fix." So we'll start with that. Just as a side, I'm with Trane Technologies, but I'm speaking today as an ASHRAE Distinguished Lecturer, and we'll be talking more about some ASHRAE publications, resources for you later. Next slide. Many of you indicated that you're not really familiar with ice storage. This is a central energy plant at one of our high schools. The building in the back holds two 500-ton centrifugal chillers, and those round cylinders sitting there are ice tanks. Those are basically filled with water, and there's a small plastic tubing inside that circulates a water and glycol mixture at 24 degrees Fahrenheit that will freeze the ice, and then we freeze it during the night. And during the day, we reverse the process, and we're able to provide cooling to the entire campus and avoid running the chillers during the day and incurring electric demand charges. A little about Brevard County Public Schools. It's the 50th largest school district in the United States, 75,000 students, 9,000 teachers and staff, 13 million square feet, 84 schools, 20 of which have ice storage. And we were spending $11.5 million a year on electricity, averaging 10 cents per kilowatt hour. And I'll just throw this in there. The rates were $13 per kW per month, 8 cents on peak, and 5 cents per kilowatt hour off peak. Next slide. The reason that Brevard schools put so many ice tanks in is the local utility really promoted them. They have a very, very lucrative $600 per kW for new ice storage systems. They also took care of life cycle costs. If you had to replace a tank, if you had to refurbish a tank, and they made it very simple. They just assume all air-cooled chillers are 1.19 kW per ton, and that all water-cooled chillers are 0.68. No measurement verification, no in-depth testing. It was simple, easy, and a great program. For those of you who aren't familiar with ice storage, here is your round tank. They have round tanks and they have rectangular tanks. The round tanks are made of plastic. The rectangular tanks are made of steel. These tanks, as you can see, are heavily insulated using a styrofoam on top, on bottom, all around it. Very little energy loss. Very efficient, good round trip efficiency. Inside the plastic tubing, there's 3 miles of plastic tubing circulating a water glycol mixture. It freezes the ice, and we reverse the process to cool the building. Next slide. The concept is really very simple. Most commercial buildings, schools, and office buildings are unoccupied at night. The chillers are turned off, and we can use them at night to build ice. Typical commercial building, someone comes in at 6 a.m., they turn on the lights, the air conditioning, and the computers, and the electric meter starts screaming. During the day, you have the warmer outside, so the chiller picks up more and more load, and ultimately the chiller is going to contribute about 40% of the peak electric demand for the building. It's very expensive power being used during that time. There is the on-peak energy charge, and more importantly, there's the demand charge, or $13 per kW per month. And it's significant. The intent is, instead of making ice or providing cooling during the day, let's make ice at night and turn the chillers off during the day. And it's huge dollar savings. It doesn't really save energy. Making the ice, you're operating at a lower temperature, so there's a slight energy penalty. However, you're making ice at night. The ambient temperatures are much lower, so it's basically a wash. Next slide. We've been using ice to cool buildings for a long, long time. Ice used to be collected or harvested in the winter from lakes in the northern United States and shipped everywhere by rail. Well, we don't do that anymore. Instead, we're making ice in the building. And we've been doing this for 30 plus years. We've had a system up there that existed for 40 plus years. Next slide. So why are we going to put in thermal storage? Again, it's about saving money. It's about reducing your peak demand charges. You can save 25% of your cooling costs by incorporating energy storage. And then if you have a utility who's helping out, you can get a payback of 3 to 5 years. You're gold. You're else in the school district or a local government, are you going to save that much money? There are other benefits to having thermal storage systems in. One, during off-peak periods, I should say off-seasonal periods, your chiller plant is running at very, very low loads. It's cycling on and off. That's terrible. That's how you burn out a chiller. Using ice storage, I make ice at night and I use the ice during the day, and I don't have to cycle the chiller on and off. You also have redundancy. If I have a full storage system, it will produce cooling for 8 or 9 hours. If my chiller goes down, I have 8 or 9 hours to fix the chiller or find an alternative. The big one for us, though, is resiliency, and that's defined as recovering from a catastrophic event. If you look at the screenshot on the left, this is from a big chiller plant, and you can see it's having a series of problems over the month. Power supply, power failure. Part of the reason for that is Florida is the lightning capital of the US. We have serious number of hits every single summer. When a lightning bolt hits, it sends a surge to the entire grid, and it's going to trip the protective circuits in the chiller. We could automatically restart it, but we don't. We want to ensure that that very expensive chiller is operating safely, so we send a technician out to do a manual restart. So a fun story. School starts in August down here in Florida, and the first Monday of the school year, the phone's ringing off the hook. I've got 14 screaming principals saying, we don't have air conditioning. Obviously, the lightning hit over the weekend. We send a technician out. Then the next Monday, the phone's ringing again. Same problem, and people are not happy about this. The third Monday in the month, the phone's ringing, but this time it's not the principals, it's the police. It seems that all the students got up and left. If you can imagine thousands of students leaving school unsupervised, yeah, you have a problem. What we noted, though, is that the schools that had ice storage systems did not have students leaving. Why is that? Well, because as you have power, you can run your pumps and your fans, and if you got ice sitting back there, you can cool the building. The only problem would be in the afternoon, if you burned all your ice, you might have to turn the chiller on during a peak period and get slammed with a demand charge. Next slide. First thing you learn working in schools is that you're always going to have challenges. Personnel turnover, trying to find qualified people who understand the technology. Everything is low bid. You're trying to rip everything out and get it back in line in a 2-month period. There's never any money for budgets, for repairs. And the maintenance department is not motivated to save money. They're motivated to just reduce the number of complaints. So that said, when I came on board with the school district, and I looked at our 20 ice plants, I found that 11 of the ice plants were working great after 20 plus years. It's pretty amazing. These things were reliable. They just chug along, saving money. And as I said, they had a payback of 3 to 5 years. These things are now operating for 20 years with virtually no additional investment. Fabulous story. Some were having problems. Some were severely neglected. The big one I found was 3 of the schools had just had their controls ripped out and put new controls in, and they couldn't make ice. That didn't make sense to me. Making ice is very simple. You just change the control set points. Nothing good here. But unfortunately, they were paid and never fixed it. 3 of the schools that had rectangular tanks had structural damage. This is after 20 years, so they more than lasted a long enough time. But we decided to replace one school system with the circular tanks, and we got a huge rebate from the utility. And then the third had glycol leaks, so we know we could figure out how to fix these things. So we called the manufacturer, had to come down and talk to us for a little bit. Lo and behold, simple solution is rip out the old tubing, put new tubing in, and the utility would pay for it. Great solution. We identified that we could save an additional $1.6 million a year by making these small little changes. Unfortunately, COVID came in and, well, things kind of like went south. What I want to point here from best practices, number 1, qualify your controls vendor. You don't want somebody doing your controls who has not done a thermal storage job before. Reach out to your thermal storage vendor. See if he's got any updates. It's kind of like, oh, go to the factory authorized car dealership and see what recalls have been. Look at remote monitoring. It's simple, it's easy, it's cost effective, and you can have experts taking a close look at it. And then find some way for the easy fixes. Next slide. The big change we're seeing is the emphasis on small package systems. You know, big projects, you can afford to have a lot of engineering, a lot of team put together, but on small systems, you really want to make it simple, you know. And when you look at these systems, you consist of a chiller, your tanks, and then everything else, or as we call it, the completion package. Instead of having everything field erected, but have it factory assembled, shipped to the site, make it simple to connect, plug and play. And again, we're at that point now where remote monitoring and diagnostics will make life easy. So let me shift gears here. Next slide. We're seeing big changes in the utility industry. We are going through a transformation. We're moving from fossil fuels to renewable energy. Fossil fuels, greenhouse gas emissions, we're going to move away from them. Renewable energy, it's fabulous. The only problem is it's intermittent, meaning it doesn't always, the sun doesn't always shine and the wind doesn't always blow. There will be shortages, and we're seeing that. But from the utility industry, that's not the big issue. Down the road, what's going to be a concern is when they have too much solar and too much wind. They're going to have to find a place to put it, okay? They just can't turn your solar system off. They've got to take it somewhere. Oh, of course, no, batteries will solve that problem. Well, have you tried to price a battery lately? They are underdeveloped. I don't want to say anything further than that, but it's not really cost effective yet. Next slide. So in case you haven't heard, we passed the Inflation Reduction Act in August of 2022. Massive financial bill, $369 billion for clean energy and climate change. I just said it's massive, but it really doesn't change a lot of things. What it did is extended the tax credits for wind, solar, geothermal, electric vehicles. They all had a 30% tax credit. They still do. But there are three major changes I want to highlight. First and foremost, they finally realized that energy storage is absolutely essential if we're going to have 100% renewable energy by 2050. And so they want to incentivize it. They've given energy storage that same 30% tax credit. And they specifically included thermal energy storage or thermal batteries as qualify for that 30% tax credit. Additionally, they want to see all of these energy technologies manufactured in the United States. So they have a bonus 10% tax credit if you meet a certain US domestic content. And most of the thermal storage systems manufactured here in the United States will meet that. We get a 40% tax credit. And finally, in the past, schools and local governments couldn't take advantage of those tax credits. You have to pay taxes to get a tax credit back. Well, they changed the rules. You no longer have to pay taxes to get that tax credit. You can get that directly from the IRS by filing a 3468 form. Next. This is a game changer, okay? Again, 30% tax credit for energy storage, including thermal storage, a 10% bonus for US content, and schools and local governments qualify. And it's not just for the storage tanks, it's for the entire system, the controls, the completion package, and the ice-making chiller. And because of that, chillers with storage are going to be 25 to 30% less expensive. Next slide. I want to spend a lot of time talking about economics. I don't have that window right now, but here's an example looking at a 25,000 square foot building, roughly 600 tons in Minneapolis. I'm going to look at a conventional chiller, partial storage, full storage, look at the tax credit, and look at a rebate. Next slide. This is a pretty confusing graph, but let me see if I can walk you through. The little black dots is the load profile for the conventional chiller, and it tops out at 600 tons. The alternative now is to go to a full storage ice storage system, where I will produce the ice in green. And I start that at 10 p.m. at night, run it till 7. And then I switch back to running the chiller as a chiller and using the ice to supplement that to meet my load profile. And then at 2 o'clock, I will fall into the peak period for that utility, and I shut the chiller down and just use ice. In this case, I was able to downsize the chiller to 441 tons. I had to put in a whole bunch of ice, roughly 19 tanks, but I have a 0 peak KW. Next slide. Here we compare the cost of these systems. The conventional chiller, I have 600 tons. It's going to cost $900,000 to put that in there. And there are no utility cost savings because that's my baseline. I jump to partial storage. I can downsize to 330 tons of air-cooled chillers. I need to put a little bit of tanks in. I save some money, and I have a pretty high premium over the conventional. However, I'm saving $54,000 a year. It's about a 5 to 6 year payback. It's not bad. But here's the game changer. If you look at that tax credit at the bottom, I get 40% of that $1.2 million back. Okay, nearly $500,000. That makes this system the lowest cost system out there. There's no payback. It's great. Similar to full storage, a little more for the chiller, a little more for the tanks, a lot more savings. And look at that tax credit. Of these two, which is better? Well, I'm not sure. This is based on today's electric utility rates. I think that's going to change. I think electric vehicles, I think batteries are going to have a big impact on what you're going to pay for electricity in the future. And I like having as much flexibility as I can have. I'd be incorrect here not to point out that big sign in red. Disclaimer. Okay, consult your tax advisor for your particular project. Hey, I'm an engineer. I'm not a tax whiz. I'm not a tax expert. Do yourself a deep favor. Next slide. This is my wrap up. Where's things going for the future energy storage? Well, we pointed out already, the transformation of the utility industry from fossil fuels to renewable energy. We are going to have shortages, but more importantly, we're going to have surplus down the road, and we need a place to put that surplus. And electric batteries are ultimately going to be the place we want to work at. But for now, we're thinking thermal batteries, which have been proven, reliable, and cost-effective, might be the first phase to consider. Okay, it's 1/5 the cost of an electric battery. If you look at that vehicle on the right, what is that? That is a what is that? That is a hybrid automobile, gasoline and electric batteries, very efficient, very clean, and growing. Why not do the same thing with hybrid buildings, having hybrid batteries, both thermal and electric? Thermal batteries to take care of the thermal loads, electric batteries to take care of the fans, the lighting, controls, what have you. We think that's going to go a long way. Just a quick shout out to NREL. They just released a report looking at hybrid batteries and strongly recommend both systems. So that said, I'll take this opportunity to say thank you very much. Next slide. And I'll look forward to trying to get back to you in the Q&A session. Thank you.
So now I'm to introduce Ken. Kent Marsh is an experienced vice president with a history of working in higher education for Colorado Mesa University now. He serves as the VP for Capital Planning, Sustainability, and Campus Operation. A strong professional engineer with a Master of Business Administration and over 25 years experience in operations management, business management, construction management, sustainability, building and grounds maintenance. Kent has worked with the leadership team at CMU over the past 15 years to construct a single pipe geothermal system that heats and cools 1.2 million square feet, saving the university $1.5 million annually, while reducing their carbon footprint by over 10,000 metric tons per year. Please, Kent.
Marcus, thank you. Good morning, everyone. Well, it's maybe good morning or good afternoon. What I'll say about Geo is start with a little joke. I will say that the university started installing our system back in 2008. Really, we were geothermal or geo exchange before geothermal and geo exchange was cool. We're very pleased at Colorado Mesa University that our system is now being recognized across the country. And I've got to say, this has been the fourth or fifth presentation that I've had the pleasure of giving over the last 12 to 18 months. So thank you to NREL and the DOE for allowing me to be part of this webinar. If you'll change the slide, please. So I'm going to start with a brief description of our system, and I've got 10 or 15 slides where I'll try to dig into the details of each of these components. But I'll start by saying that the major components that our thermal energy storage system is made up of include a drill field, and not just a single drill field. Colorado Mesa University has 8 total drill fields on our campus, the first of which we installed back in 2008. Those drill fields, the easiest way to describe a drill field is they're all located beneath green space across campus. We also have some drill fields that are beneath parking lots on campus. Colorado Mesa doesn't build buildings over drill fields, although I think you can. There are other parts of the country where drill fields are, where buildings are built on top of drill fields. But for now, we're not doing that. Basically, a drill field is an area where we will drill a hole in the ground up to 500 feet deep. And within that hole, we install a piece of looped pipe that's connected at the bottom. And that pipe is 1.25 inches in diameter. And we shove that pipe 500 feet into the ground and we surround it with thermally conductive grout. And that allows us to move heat between our system and the ground, or to grab heat from the ground and move that heat into our system. Those drill fields are located 25 feet apart and are all connected together via a header system. Another major part of our system includes high-density polyethylene pipe. We have miles and miles of that stuff, and that really defines what we call our central loop. And our central loop is the system of pipes that allow us to connect all of these drill fields together and to be able to provide that resource to buildings across campus. Within each of those pipes that I described, both in the drill field and in the central loop, those pipes are filled with water. Water is the medium that we use to move heat around campus, and to move that water through our system requires pumps and variable frequency drives, and we have several pumping stations across our campus. We have many plate and frame heat exchangers, and those heat exchangers are used to move heat from water loops that we have within a building into our central loop, or to move heat from the central loop into a building. They're also connected in locations where we have cooling towers that allow us to dump waste heat to the air around a building if our system ever gets too warm over the summer. We also have heat exchangers that allow us to add heat to our loop via some boilers across campus. And really the star of the show are the magical boxes that we install inside buildings that allow us to move heat from the indoor air into the building loop, and from that building loop potentially to another building via our central loop, or allows us to extract heat from that building loop and dump that heat into the indoor space within a building, and those are heat pumps. And we have many, many of those across campus. Next slide, please. So our system is comprised of, as I mentioned, 18-inch diameter HDP pipe down to 1.25 inches. We've got a lot of areas that are 10 and 12-inch diameter pipe. It really just depends on the load of that part of the system. We'd like to keep the flow rate within the pipes at or below 5 feet per second to keep our friction loss as low as possible. We have about 2.5 miles of central loop piping, if you can believe that. It seems like that's a huge number, but we have a lot of it on campus. We have 8 separate drill fields, as I mentioned, 427 holes that are drilled up to 500 feet deep. I know that 1,000 heat pumps is a big number, but when you think about a 55,000 square foot building, on average, that has between 80 and 90 heat pumps. So when we have 1.2 million square feet of buildings connected, that's a heck of a bunch of heat pumps. I mentioned the cooling towers. We have 5 cooling towers, and these cooling towers we use to dissipate waste heat during the hottest couple of months of the summer if we need to. Over the last couple of years, I haven't needed to turn those on, which is wonderful. We also have some supplemental boiler plants, and we have 2 of those that we can add waste heat, or we can add heat to our system if we need. And then we have pumping stations. We have several of those across campus. And I've got a graphic a little further down the road in my slides here that I'll show where some of those attributes or those assets are installed in our system. Next slide, please. So I'm going to do my very best to describe a drill field. And this picture up on the upper left corner is a picture of the very first drill field that we installed. And you'll see that it's below some green space on campus. The field in the forefront and the field that's further towards the top of the page, which is actually to the south on our campus, is also drilled. And each one of those dots represent the hole that we drill 500 feet in the ground, and we install that 1.25 inch diameter pipe. And then out of one hole, we run that pipe over and down into another hole that's spaced 25 feet apart, and so on and so forth. Each of those drill fields, or those holes in the drill fields, is connected into a header. And you'll notice in the picture at the lower right of the screen, that's a picture of what look like either 6 or 8 inch diameter pipes that connect those holes we drill in the ground into a central loop pumping station. Next slide, please. I'll mention that our drill field, we've installed deep enough beneath the ground to prevent us from having to install glycol. We have many hundreds of thousands of gallons of water in our system, and we didn't want to have to add glycol to the system to prevent it from freezing. So we make sure we install our system below the frost step here in Western Colorado. The picture in the upper left corner is another picture of some pipes that are leading to the header system out in a drill field. And the other 2 pictures are of the technology that we use to drill 500 feet into the ground. That picture of the drill field, I swear that machine was from World War II. It was, I don't know how old, but crazy, crazy old, not very efficient, wasn't very fast. We've kind of moved from that to the system, the trucks that are shown in the lower left picture. And those trucks were truck mounted drilling rigs, and they used air to drill into the ground, and they were much more efficient. We were able to drill much faster and get those parts of campus back online sooner than we were able to with that earlier type of drilling system. Next slide, please. So how does our GeoExchange system work? Really, our system, all our system really does in the most simple sense is it allows us to move heat energy that we either extract from the ground and put into our central loop, or heat energy that we extract from a building and move into our central loop where it's moved to another building, or potentially where we dump it into our 800,000 gallon swimming pool. Or we move it back into the ground. And how this works is on a day like today, if we were in session and we had 100 students in a lecture hall, let's say on the south side of a building, which right now would be in full sun, we're probably cooling that space. And so within that building, we have a water loop. And that water loop allows those heat pumps in that lecture hall to extract that heat from the indoor air and potentially simply move that heat from that lecture hall on the south side of the building to some offices on the north side of the building. North side of the building would be in shade, and on a day like today, it's pretty cold. So the first least energy path is simply moving heat from different areas within a building. Our next least energy path is the building that I'm describing may get, that loop water may get too cold because it's a cold day. And today, because we're not in session, there's no students in that building. So I'd almost guarantee that we're grabbing heat energy from the central loop, and we're using these plate and frame heat exchangers to allow heat energy to be pulled from the central loop and added to the water loop inside the building. So that's the second least energy path. And then the third least energy path is, okay, now we've extracted more heat or added too much heat to the central loop. And now we need to dump that waste heat to, let's say, our swimming pool or to a domestic hot water system on our campus, or we need to move that heat into the ground. Likewise, we could potentially need to move heat from the ground into our central loop. So those are the basic paths that we use to turn pumps on throughout our campus to move that heat between those various resources and those various assets. Next slide, please. So I've got some wonderful pictures of some of the system components. That picture on the left is a picture of a very large plate and frame heat exchanger. That particular heat exchanger is on our central loop, and that is allowing us to move heat from the building into the central loop or from the central loop into the building. Those smaller pumps in the lower right-hand side, those are pumps that are on the building water loop that I described. And really all those pumps do is move heat energy between interior spaces within a building. And in the upper right, that's just some pictures of some variable frequency drives. And so our pumps are smart. They only turn on at the speed that's needed for the load at the time, rather than turning something on and having it at full power, consuming as much power as the pump's able to consume. We're able to ramp that pump down and ramp it up to based on demand. Next slide, please. So these pictures show the central loop piping, and as you can see, that's I'm going to guess that's at least 5 feet below the ground, so we're below frost level. The big pipe is an 18-inch diameter pipe, and the smaller pipes connecting, I'm going to say those are between 10 and 12-inch diameter. And so depending on the load in any particular part of our system, the pipes that we have serving buildings within that micro loop may be as small as 10-inch, and then our central loop pipes, of course, are 18-inch diameter. Next slide, please. So how do we do this? So in order to orchestrate all of these moving parts, whether it's just turning the pumps on inside a building to circulate that heat through the building water loop, or knowing when we need to turn on the central loop system pumps to move heat from building to building, or we need to turn the pumps on that move heat from the central loop into the ground, or grab heat from the ground and move it into the central loop. All of that is controlled by our front end system, and it's a train system. And this graphic shows you, I know there's a lot going on, but really what it shows you is some of the buildings that we have connected. It also shows the location of the drill fields and the numerous cooling towers and all of the pumps that we use to circulate fluid throughout our system. Next slide, please. I'm going to probably pass on this. I've already described how our system works, and this is kind of just getting into the details of when our train system knows to turn the various pumping systems on. And if anybody has questions about this, I can certainly answer those following this presentation. If you're able to review my PowerPoint and have questions, please feel free to send me questions and I'll do my best to answer them. Next slide, please. So why did CMU decide to incorporate geothermal back in 2008? At the time, we were building a new classroom building, and the governor of Colorado had said at that point in time that any new building that was receiving capital construction funds from the state of Colorado had to be not less than LEED Gold certified. And so at the time, we decided to install GeoExchange because it was one of the most, if not the most efficient HVAC systems that we could install in a building. And from that time, the university decided that any new building or significant renovation would be connected into our Geo system. And so why did we choose to do that? Well, one of the reasons was because it significantly lowers our operating cost. And I'll talk in more detail in the next slide or two about how it lowered our operating costs. Lower operating costs on our campus keep the cost of our per credit hour tuition and fees as low as possible for our students. We also decided to use GeoExchange because we believe it's sustainable and it's eco-friendly. It greatly reduces our carbon footprint. And another reason is both myself and the other members of the leadership team and the majority of our campus believes that higher education should lead by example. And we believe that installing the system that we have in place today is something that other people can look at and say, wow, I didn't realize that a system like that existed, and I didn't realize that it was so simple to own and operate. The graphic, I'm going to do my best to describe the graphic. The graphic really shows a narrow band of electricity use based on the fact that we increased our connected load from 800,000 square feet to 1.2 million square feet, but we're able to keep our demand or our consumption of electricity within a narrow and 4 megawatts. Next slide, please. Oh, 2 minutes, darn it. I'm going to move to the next slide, talk about some economics. Next slide, please. Next slide. Let's go to the next one, please. So probably the last slide I'll be able to touch on is HVAC systems traditionally consume about 22 kilowatt hours per square foot of connected load per year. Geo system consumes less than half of that at 10 kilowatt hours per square foot. That really equates to a system that we currently save about $1.6 million per year. And with the 20 million that we've installed, we have reduced our payback from traditionally a Geo system would be around 20 plus years to our current system that has us at a payback of about 12 years. One final slide or two here. Next slide, please. Next slide. One more. I'll talk about the carbon footprint. So last slide. So this slide shows the gray area above. That's the reduction in carbon footprint over the last 12, 13 years. The orange information below shows the carbon footprint of our campus versus what our campus would have been had we installed a traditional heating, ventilating, and air conditioning system. I'm sure I'm out of time, so I'm going to stop talking. Thanks, everyone.
Thank you. Thank you. You know, the information is there for more. And obviously, those slides and the links would be available. I don't know, many of you are submitting questions to the Q&A and Slido, and I think we have a chance of answering some of those. I'm looking at some of the questions that are here that are specifically and have not been answered yet for the group. One of the questions that I like for Kent, just because you just presented, Kent, was just came up, and I started answering it. You know, the system is interesting, but what is the storage, right? It's a district energy system. And I mentioned the fact that the loop itself is a storage, but maybe you can elaborate a little bit on that, Kent.
Yeah, so the loop itself is a storage. So all of the water that we have in the system allows us to store heat. But I'll say that the ground itself is also the potential for storing heat. Right now, we don't do that, but we are planning on at the end of this summer, seeing if we can't kind of preheat the ground. So instead of the deep earth temperatures being at 54 degrees, what if we dumped waste heat in August and September and got that deep earth temperature up to 60 degrees, let's say? We could then extract that heat when we need it in the winter. So that's a technology that we haven't used yet, but we're kicking the tires on for sure.
Okay, great. Looking at some of the questions that came up, you know, we answered some of those the best way we could, but there are some specific ones that I think it would apply to everybody. One of the questions is where you get information about, you know, any IRA incentives, you know, for this kind of systems. Maybe Bruce can add something to that.
Well, first and foremost, the IRS has everything posted on their website, and specifically we're looking for IRS tax form 3468, and it covers the Section 48 tax credit. And it goes into a lot of details. If you'd like, please send me an email and I will send you the link.
That's great. Other questions? I'm trying to glance through them and actually look at the ones that we that it would be interesting for everybody to mention. One question that came up is, how does thermal energy storage actually, can be used for electrification purposes? There are like some answers there, but I'd like either one of you to start addressing that, please.
I'll jump in on the first one here, and that's we currently installed our first storage source heat pump in La Crosse, Wisconsin. This is a system that utilizes air source heat pumps, heat recovery chillers, and ice tanks to provide hot water in the winter for areas where it have prohibited natural gas for space heating. It's using technology that we've been producing for the last 3 years, so last 3 decades, and just a new application. We're expecting it to take off tremendously. It's very efficient and it qualifies for a 40% tax credit.
Would you like to add anything about that, Kent? Because the systems are very different. When you look at a district, energy system as a storage system or this one, from electrification purposes, what is your take, Kent?
So from the electrifying buildings, we certainly do that. We both heat and cool a building with electricity, whereas traditionally we would heat a building with a boiler and baseboards and cool the building with a rooftop unit. Our system is totally electrified. I think the missing piece, I don't see how our system would ever be able to generate electricity, but the missing piece to our system is solar. If we were able to produce some of the kilowatt hours that we consume in the pumps and the heat pumps that move the water throughout our system, that would increase the sustainability of our system. And again, I think lower our operating costs. But I don't believe our system in and of itself would be able to generate electricity.
Thank you. Final slide. We are out of time, but I want to at least, offer that, all of us that are on this, can you move to the last slide, please? There's a bunch of webinars that are, scheduled. Then the last one, please, which we have our faces and emails and so on. There we go. Just in case if you have additional questions, please contact us. There are many resources that you can address. Thank you so much for attending. I'll see you next time.